Light and Sound, Chapter 1, Waves, continued. Section 3 deals with wave interaction. First type of wave interaction is what's called a reflection. This is when waves bounce back after striking a barrier. So just like the picture up top, when a flashlight, the light strikes the mirror and reflects back off. Okay. Water, sound, light can be reflected. For example, a reflected sound is what we call an echo. Refraction, on the other hand, is where the bending of a wave actually passes through something and the angle is changed as it goes from one medium to another. So for example, if we were to look at the sunlight that's coming into the classroom or into your house, even though the glass is what we consider to be clear, you can still tell that there's a window there. Why? Because the sunlight is being bent just enough that we can see that second medium that is coming through. The first medium is the air, the second medium is the glass, and then the third medium is actually when it enters back into the air as it enters the room that you're in. Again, the speed at which something moves through depends on the medium. Okay. The first part enters the medium at an angle, travels at a different speed than the rest of the wave, causing it to bend. If you've ever looked at a pencil in a glass of water, this is a great example of how this works. Okay, the image down on the lower right hand side here kind of shows that. Obviously we know that the pencil is in a straight line, but if you look just right as you're looking through the glass, that image appears like it's bent almost in half or even broken in half. That is because of refraction. The next type of wave interaction is called diffraction. And this is when waves will bend around a barrier or through an opening. For example, I could be standing in my classroom, and if the door is open, you could be out in the hall or around the corner a little bit and still hear me talking. That's because my voice is diffracting the waves produced through the opening into your ears. Sound waves tend to diffract better than light, but light will to a certain extent. The amount depends on the wavelength and the size of the barrier. So example, if the band was say practicing on one side of the school and we were around the corner from them, we still would be able to hear them. That's due to diffraction. This leads us to interference. What interference shows us is that waves, because they are not matter, can occupy the same space. So the waves can share space because they are energy and not matter. Okay, so what's the definition of interference? Definition of interference is when two or more waves share the same space or overlap. Now let's take a look at the two types. The first is called constructive interference. This is when waves meet and it actually increases the amplitude. Remember, we studied amplitude early in the chapter and we know that that's the amount of energy. Okay, so therefore it's when two crests are going to actually overlap to produce a higher crest, or two troughs are going to overlap to produce a lower trough. Okay. A lot of times we use this to create music. Okay, we're creating, if we have multiple instruments, say playing the same note at the same time, it's going to increase the amplitude. Okay, that's called constructive interference. A lot of people get confused because they think of interference as being a negative thing, but if it's constructive interference, that certainly isn't always the case. On the other hand, there's destructive interference. And this would happen when crests meet a trough. So therefore you've got two waves that are sharing the same space that are kind of wanting to go in opposite directions. Okay, this is actually going to decrease the amplitude. Okay. If you look down at the diagram in the lower right hand corner, there's a couple of waves there that are showing how both of these might work. The next item is called standing waves. These are going to form between waves that are currently being created and waves that are reflecting. When they meet, it forms what we call a stationary pattern. So this is where portions of the wave are at rest due to destructive interference, meaning that when one wave is wanting to go up, the other is wanting to go down, and therefore they kind of get stuck in the middle. There are also going to be portions of the wave during a standing wave phase where the waves are going to have very large amplitudes because when the waves meet, they both are wanting to go in the same direction. Okay? That's due to constructive interference. Okay? The wave actually isn't really stationary. It only appears that way as there happens to be waves traveling in both directions. Remember, the part where it looks like it's at rest or not really moving is just because of destructive interference. It's the two waves wanting to go in opposite directions. The last piece is what is called resonance. And this is where an object that's vibrating at or near the resonant frequency of a second object causes it also to vibrate. Now that may sound kind of confusing, but really you've seen this many times. Let's look at the xylophone down at the bottom. The percussionist actually strikes the keys on top, which causes them to vibrate. That vibration then is passed to the tubes that hang underneath. Air then, as it moves through those tubes, is what produces the sound. So even though the musician never actually strikes the tubes, the resonant frequency caused by the wooden blocks that are struck by the musicianist causes the noise. The resonating object absorbs the energy from the vibrating object. The vibrating object, remember, is the one that's struck, which causes the second object to resonate, making it the resonating object. That concludes section 3. This also concludes the notes for chapter 1, waves.